You know, behind every single click, every login, every little thing you do online, there's this silent war being fought. On one side, you've got developers building the digital world we all live in. On the other, attackers are trying to tear it all down. And in the middle, defenders, working around the clock to hold the line. This is that story, the constant battle to build, break, and defend our corner of the web. To really get this battle, you have to start with one simple, kind of surprising fact. The web is forgetful. I mean, by its very design, it's stateless. So when you click from one page to the next, the server has absolutely no memory of who you are. To build anything useful, like a shopping cart or a login, developers had to basically invent a memory for it. And they did it with things like cookies and tokens. Think of them like digital sticky notes that say, hey, I remember you. But as we're about to see, giving the web a memory is exactly where all the security challenges really began.
So, here's the game plan. First, we'll look at the digital blueprint, how these applications are actually built. Then, we're going to put on our black hats and dive into the attacker's playbook for breaking them. And after we've seen the exploits, we'll figure out how to build a digital fortress and mount a real defense, wrapping it all up with a look at the modern landscape of this ongoing fight.
Okay, first up, the digital blueprint. Before you can figure out how to break something, you've got to understand how it's put together in the first place.
So at its heart, a modern web app has three main layers. It all starts with you, on the client. That's your browser. You type in a URL, and it fires off a request to the web server. Now, the server is the brains of the whole operation. It processes your request, and if it needs info, like, say, your user profile, it pings the database server, which is basically the system's long-term memory. The data flows back, the server builds a response, and boom, your browser displays the final page. And this brings us right back to that stateless problem. On the left, you see the classic solution, a session. It works kind of like a coat check. You log in, the server keeps your info safe and just gives you a simple little ticket, a cookie with an ID. On the right is the modern way, a token. This is more like a VIP pass. It has your information right on it, all cryptographically signed. The server doesn't need to remember you, it just has to check the signature on your pass. Tokens are way more efficient, but think about it. If someone steals your simple coat check ticket, they just get your coat. But if they steal that detailed VIP pass, they might get into the whole party, as you.
All right, we've seen the blueprints. Now, let's flip the script. How do attackers look at this well-structured system and find the cracks to break it wide open? Here's a really key insight into an attacker's mindset. They know that no system is perfect. They're not just looking for random bugs, they are hunting for predictable patterns of failure. So let's dissect their playbook, starting with what is, without a doubt, the #1 vulnerability on the web: broken access control. This is probably the most common vulnerability out there, and it is shockingly simple. An attacker logs in and sees their user ID in the URL, maybe something like user/123. So what do? They just try changing it to user/124. Now, if the server doesn't do an authorization check, if it doesn't stop and ask, wait, is user123 allowed to see user124's data? It'll just hand over that private information. It's the digital equivalent of an entire apartment building where none of the doors are locked. So the fix is pretty straightforward. You lock every single door. The server has to act like a bouncer for every single request, asking not just, are you logged in, but also, are you actually allowed to be here? This means checking permissions on the server every single time. Another really smart move is to use unpredictable IDs. You know, long, random strings instead of simple numbers like 123. That makes it nearly impossible for an attacker to just guess their way into someone else's account. Let's move on to another classic attack, SQL injection. This is where an attacker literally gets the database itself to spill all its secrets. Look at the flaw here. The application is just blindly sticking user input directly into a database query. So the attacker provides a username, but they sneak in a little bit of SQL code, R or 1 equals 1. While since 1 always equals 1, the entire condition becomes true for every single user in the database. The database then just returns all of its data, completely bypassing authentication. The defense here is all about one thing: separation. Instead of mixing user input with database commands, developers use something called prepared statements. Think of it like this. First, you give the database the command template with a placeholder, like find the user where the name equals blank. Then, in a separate step, you hand over the user's input. The database treats that input only as data to fill in the blank, never ever as a command. This simple separation makes it impossible to trick the database. So, the attacks we've looked at so far really target the server's logic.
But there's another whole class of vulnerabilities that target something way more fundamental: the chain of trust between you, your browser, and the websites you visit.
Cross-site scripting, or XSS, is a complete betrayal of that trust. Here's how it works. An attacker injects a malicious script onto a legitimate website, maybe in a comment section or a forum post. Later, when you visit that page, your browser, which trusts the site, just goes ahead and runs the script. And look at this example payload. This simple script grabs the victim's session cookie and sends it to a server controlled by the attacker. Just like that, the attacker can pop that cookie in their own browser and completely impersonate you.
Now, defending against XSS takes multiple layers. The main defense is to always treat user input as plain text, never as code that can be executed. But there's a brilliant second layer of defense called the HTTP-only flag on session cookies. It's a simple instruction to the browser that says, hey, this cookie is off limits to JavaScript. It acts like a protective shield, making it so much harder for a malicious script to steal a user's session.
Okay, now for one of the absolute sneakiest attacks: cross-site request forgery, or CSRF. Check this out. You log into your bank, and your browser holds onto that session cookie. A little later, you visit a different, malicious website. Hidden on that page is some code that forges a request to your bank, let's say to transfer money. Your browser, just trying to be helpful, automatically attaches your bank cookie to that forged request. The bank sees a valid request with a valid cookie and just processes it. The transfer goes through, and you never even knew it happened.
Luckily, modern browsers have a really powerful defense for this. There is a cookie attribute called SameSite, and it basically acts like a border guard. It tells the browser, only send this cookie if the request is coming from the same website that gave it to you. So, in our bank example, since the forged request came from evil.com, not bank.com, the browser would just refuse to send the cookie. The attack is stopped dead in its tracks.
Okay, we've spent a lot of time inside the attacker's playbook, so let's switch hats. Knowing all of this, how do we actually build the digital fortress? How do we create a solid defense?
Well, this is the Defender's Toolkit. For every major vulnerability, there's a specific countermeasure. To stop SQL injection, you use prepared statements. To block those forged requests, you implement same-site cookies. To neutralize malicious scripts, you use a content security policy. It's a strategic map, connecting the problem directly to its solution.
Let's just zoom in on one of the most powerful tools in that toolkit, a content security policy, or CSP. Think of it as a really strict whitelist that the server gives to the browser. This policy says you are only allowed to load scripts and resources from these specific trusted domains. So as you can see here, when an attack tries to inject a script from an untrusted source like evil.com, the browser just checks the list, denies the request, and the attack is neutralized before it even has a chance to run. So, after exploring this whole cycle of building, breaking, and defending, what does the security landscape really look like today? I mean, where are we winning and where are the biggest challenges? Well, this isn't just some random collection of flaws. The security community actually prioritizes these risks using frameworks like the OWASP Top 10. You can think of it as the industry's official most wanted list for vulnerabilities. It tells defenders exactly where to focus their energy. And as you can see, the issues we've been talking about, broken access control right there at number 1 and injection at number 3, are the very things keeping security pros up at night. So what's the good news? We have some incredibly powerful weapons. Modern development frameworks have defenses built right in, and browser security has come such a long way. But the biggest challenge, the one that persists, is complexity. And there's a reason broken access control is still number 1. It's not really a deep technical challenge, it's a flaw in human logic. And that's a much harder bug to patch. So let's do a quick recap. What are the key takeaways from all this? We learned that we use cookies to give the forgetful web a memory. We saw how attackers use XSS to inject malicious code into websites, and SQL injection to trick databases into giving up their secrets. And we know that the OWASP Top 10 gives us that strategic map to fight back effectively. And all this brings us to our final question. The web is only getting more complex, more interconnected, and with every new piece of technology comes a whole new set of potential vulnerabilities. This battle between building, breaking, and defending, it's a constant cat-and-mouse game. Which leaves us wondering, as our digital world grows ever more complicated, will our defenses ever truly be able to catch up to the sheer creativity of those who want to break them?